In the last video, we saw that we could rewrite Newton's second law applied to rotations as the net torque equals dl dt. And for a lot of cases, we could turn that into I alpha if we liked. So now let's think about the situation where there is no net torque. So in the absence of a net external torque, if the net torque is zero, that means dl dt is zero. That means L isn't changing. So that means the final angular momentum has to equal the initial for some process. Now keep in mind that no net external torque doesn't mean that there aren't forces, because remember, you can have zero torque if the lever arm is zero, even with there being a force. So let's go and just take a look at this example real quick here. Let's say you got yourself a horizontal surface, a tabletop, let's say. You've drilled a hole through your tabletop like this, and you've got a string hanging out. Let's say it's a big table. Let's say it's a 1 meter string. You got a mass hanging out over here, and you've got it spinning around in a circle like so. So you then get underneath the table and you pull on the string so that now the mass is half a meter out and it's going around like so. So let's say that our initial angular velocity was 10 radians per second. What we want to find out is what is our final angular velocity. Well, what we can do here is we can say L final equals L initial. And here you should be able to convince yourself via the hitchhiker rule that both angular momenta are pointed out of the monitor, so in the z direction. So we can just go ahead and take the z component of it and say L final equals L initial like that. And what have we got? It's going to be I final omega final equals I initial omega initial. Now, since we're treating this as a point mass, we remember that the moment of inertia of a point mass is mr squared. So this will be m, the mass doesn't change, so no need for a subscript there, r final squared omega final equals m r initial squared omega initial. And good thing the m's cancel because I never gave you the m's. All right. So we can solve for omega final to get r initial over r final quantity squared omega initial. So this will be 1 meter over half a meter squared times 10 radians per second equals 40 radians per second. Now, you should try to convince yourself that there is no net external torque here. We can neglect for the moment gravity pointing into the monitor and the normal force pointing out of the monitor. They do exert torques, but they are oppositely directed with the same lever arm, so they'll cancel. The main thing we have to worry about here is the force due to tension. Now we see that the line of action goes right through the hole we drilled, our axis of rotation. So that makes the lever arm zero. So the torque is zero, even though the tension is not zero. So there is a net force, but there's not a net torque here. Now, a quick moment's reflection, though, should maybe lead you to be just a little bit concerned. Let's think about the rotational kinetic energy before and after. So K rot initial will be 1/2 I initial omega initial squared, and K rotational final will be 1/2 I final omega final squared. So this will be 1/2 mr initial squared omega initial squared, and this is 1/2 mr initial, final squared omega final squared. All right, so let's just go and get ourselves the ratio of the final rotational kinetic energy to the initial. So this will be 1/2 mr final squared omega final squared over 1/2 mr initial squared omega initial squared. All right, so we can cancel some halves and some m's. I guess that's good. And what are we left with? We are left with r final over r initial squared times omega final over omega initial squared. Well, we saw from before that r final was 1/2 meter. R initial is 1 meter squared. But our omega final was 40 radians per second over an omega initial of 10 radians per second squared. Now all the units cancel out here. This is 1/2 squared, which is 1/4. But this is 4 squared, which is 16. So our rotational kinetic energy increased by a factor of 4. So the question now is where did the extra energy come from? Pause the video and get back with me. All right, so a guiding principle that one of my professors told me when I was first learning this is that only something that eats breakfast can do work. So you always have to sit and think about what's the thing that ate breakfast. And by that he meant that you could be talking about burning fuel too. But I'd said you got under the table and you pulled the string. So when you pulled the string, what you did was you caused the force due to tension to do work, moving the mass from here to here. That's a force with times the displacement, right? And so that turns out to be where the extra rotational kinetic energy came from, was you doing work pulling on the string to make it go faster. So in this case, the energy isn't conserved, but there was no net torque, so the angular momentum was conserved. All right. So what I've got here is I'll be showing you a video clip. In fact, I'll do this a few times. I'll be showing you a video clip, and I want you to think about why you're seeing what happened through the lens of angular momentum conservation. All right, so for this first one here, this often gets called the ice skater demo. I was standing here holding, well, my legs were definite. Trust me, my legs, I wish I could spread my legs out. We'll be realistic there. All right, so I was holding a couple of weights and I was spinning. And then, so this is the before and after. I had the weights closer to my chest. Like that. And we saw that I was spinning much faster. All right, so again, it's the same deal. The only forces acting on me are the normal force, me plus the weights, that's our system, are the normal force up, gravity down. They are aligned with each other and they go through my axis of rotation like so. So they don't exert any torque. So so this means that the angular momentum is conserved. So we can say L final equals L initial. So this will be I final omega final equals I initial omega initial. So my final angular velocity will be my initial moment of inertia over my final moment of inertia times my initial angular velocity. So the deal here is that since I'm made the mass more concentrated towards the rotational axis by bringing the weights in, this makes I final less than I initial. So that makes this fraction here a number bigger than 1, and I end up spinning faster. And again, that means my rotational kinetic energy did go up, and it did that because my muscles were doing work to move the weights closer to the center. So ultimately, the food I ate released some chemical energy to allow me to go and move the weights closer in. That's where the additional energy came from. All right, so with that, I would now like you to do the same kind of process with this clip. All right, this example is one that gets called a reaction wheel. So the deal here is that before you've got me and the wheel. And the angular momentum initially is 0 because neither the wheel nor I are spinning. So afterwards, let's say the wheel spun like this, then that would mean that I would spin. Boy, that was terrible. Yeah, well, it means I would spin. It's actually probably pretty realistic. That means that I would spin the other way, slower. But the thing is, the initial angular momentum is 0, and so the final has to be as well. So the final angular momentum has to be the angular momentum of the wheel plus the angular momentum of me. And that has to be equal to the initial angular momentum, which was 0. So that means the angular momentum of me is the negative of the angular momentum of the wheel, which makes sense because the wheel's spinning one way, I'm spinning the other way. This actually gets used in spaceflight for doing things like pointing satellites. You don't want to needlessly burn fuel because the fuel that you carry in a satellite is mass that could have been expended on making more instruments for the satellite. So you want to hang on to the fuel strictly for repositioning the satellite. But for just plain changing which way it's looking, the usual thing is to have 3 sets of these massive wheels, one aligned with the axis along the X, another along the Y, another along the Z. And motors, which are attached to the body of the satellite, will spin up the wheel. And by conservation of angular momentum, if you spin the wheel one way, the satellite has to spin the other way. Now, the energy to do that came from the batteries, which were charged by the solar panels, so you didn't expend any fuel in the process. And then to bring it to a stop, you just quit spinning it, and the angular momentum of the wheel goes to zero, so does the satellite, and the satellite quits spinning around. So this is how they change how a satellite points, so that they can point their instruments whichever way they want to without having to waste any extra fuel. All right, and to finish up here, I want you to go ahead and take a look at this video clip and do the same thing. All right, so in this one here, so before, I'm holding the wheel like so. So the wheel already has some angular momentum. I don't, but there's my L initial. Now when I flip the wheel, assuming the wheel is spinning like that, when I flip the wheel, so that's now spinning the other way, the final angular momentum has to be the same as before. But now the angular momentum of the wheel points down, and so in order for this means I have to spin with double the angular momentum, so that this plus this equals that. Thus, I end up spinning in the same way the wheel was spinning before I flipped it, in order to keep the angular momentum conserved. Alrighty. So with all of that, in the next set of videos, we will be transitioning over to thinking about Newton's theory of gravity and thinking about planetary motion. So we'll see you over there.